When you think about the sun, you probably imagine something massive, bright, powerful, the center of our solar system. But what if I told you the sun is actually pretty small? Out there, in the vastness of the universe, there are stars so big, so unbelievably gigantic, that if one of them sat where our sun is right now, it would completely swallow Mercury, Venus, Earth, Mars, and even Saturn, stars that make our entire solar system look like a tiny dot. And one of the largest ever discovered is called Stephenson 218. Some scientists believe it might be the biggest star in the entire universe. But is it really? Or are we just seeing a small piece of a much bigger picture? Today we're going on a journey to find the true giants of the cosmos. We'll discover how they form, how they grow to impossible sizes, and why even the title of the largest star might not be so easy to give. Because the more we look, the more the universe surprises us. Hello and welcome. I'm Orion, coming to you from Infinite Universe NTH, where curiosity fuels the journey and every question opens another door. Feel free to subscribe if you'd like to keep exploring with me. Every star you see in the night sky, from the smallest red dwarf to the largest supergiant, was once a cold, invisible cloud of gas. Stars are not born bright. They begin in darkness. In the vast spaces between stars, clouds of hydrogen and helium drift slowly for millions of years. These clouds are called nebulae, and they are the cradles of new suns. Most of the time, nothing happens, but sometimes something disturbs the balance. A nearby supernova, a passing star, or a wave of galactic pressure. And when that happens, gravity takes over. The cloud begins to collapse, slowly at first, then faster. Atoms pull together, tighter and tighter. The temperature rises, the pressure builds, until finally, in the center of the collapse, the atoms begin to fuse. Hydrogen atoms smash into each other and become helium, releasing enormous amounts of energy. This is nuclear fusion. It's violent, it's radiant, and it marks the first breath of a newborn star. This young star, or protostar, is still unstable. It flickers, it spins, it battles gravity, pushing outward with light and heat. But eventually, it finds balance. The gravity pulling in and the fusion pushing out reach a perfect equilibrium. And just like that, a star is born. It enters the main sequence, a phase that, for many stars, can last billions of years. Our own sun is right in the middle of this stage, but not all stars are created equal. Some are born with more mass, a lot more. And these stars, they live fast and die young. They burn hotter, brighter, and much more violently. Their lives are shorter, but far more dramatic. And some of them will become giants, truly colossal beings of fire and light, so massive they make the sun look like a spark next to a bonfire. But what do we actually know about these giants? What have we seen, and what have we only guessed? Let's meet the largest stars we've ever found. We've now seen how stars are born, but once in a while the universe creates something different. A star so large, so vast, that it breaks our sense of scale. Let's meet the giants. One of the first contenders was VY Canis Majoris. For years it held the title of the largest known star. Estimates once placed its radius at nearly 1,500 times that of the Sun. That's big enough to engulf the orbit of Jupiter, and then some. To picture it, imagine the Sun as a basketball. VY Canis Majoris would be a hot air balloon, one so massive it would float past Saturn. But science is always moving. In 2012, astronomers found something even bigger, UY Scuti, located around 9,500 light-years from Earth. This red supergiant appeared to dwarf even VY Canis Majoris, with early estimates suggesting a radius of over 1,700 times the Sun's. UY Scuti became the new heavyweight champion. If placed at the center of our solar system, its outer surface would reach far beyond Saturn, possibly touching Uranus. It was a record-breaking moment, but records in astronomy don't always last long. When more precise measurements from the Gaia Space Observatory came in, things changed. Gaia helped scientists calculate UY Scuti's distance more accurately. And with that came a surprise. It wasn't as big as we thought. New estimates brought its radius down to around 900 solar radii. Still huge, but no longer the biggest. So, the crown passed on. Enter Stephenson 218. This red supergiant is located roughly 19,000 light-years away, in a cluster of massive stars. But Stephenson 218 didn't just beat the others, it crushed the competition. Its radius? An estimated 2,150 times that of the Sun. That's enough to completely engulf Saturn's orbit, and most of what lies beyond it. To circle this star at the speed of a jet plane, it would take over 900 years, non-stop. That's not a sun. That's a floating solar system. And yet, this raises a question. Is Stephenson 218 truly the largest star we've ever found? Or is it just the one we've measured best? Because the deeper we look, the harder it gets to tell where the star ends and where illusion begins. Stephenson 218 may be the largest star we've ever found. But how do we even know that? Measuring something that's tens of thousands of light-years away isn't exactly straightforward. We don't have a ruler long enough. We don't send probes to circle its surface. So instead, we rely on light. But here's the problem. Light lies. It stretches, it bends, it dims. It gets blocked by cosmic dust, by gas, even by other stars. And the farther that light travels, the more distorted it becomes. Imagine looking through a fogged-up window, trying to guess the size of a fire burning miles away. That's what astronomers face every time they try to measure a star like Stephenson 218. To estimate a star's radius, we need to know two key things: how bright it truly is and how far away it really is. But both of those numbers are tricky. Brightness depends not just on a star's actual energy output, but also on how much of that light is reaching us. If a thick cloud of dust is in the way, a giant star can look like a small one. And the reverse is also true. As for distance, we use parallax, measuring tiny shifts in a star's position as Earth moves around the Sun. It's precise, but only works well for stars within a few thousand light-years. Beyond that, we rely on models. We compare colors, temperatures, and brightness to stars we understand better. But this introduces uncertainty. Small changes in distance estimates can result in huge differences in calculated size. UY Scuti is a perfect example. When we thought it was farther away, it seemed enormous. But once Gaia measured its position more accurately, its size estimate dropped by almost half. So when we say Stephenson 218 might be the biggest, what we really mean is, based on the light we're getting and the models we're using, it's the largest we've calculated so far. But that doesn't mean we're wrong. It just means we're working with limited tools to understand something unimaginably vast. In astronomy, truth is often hidden in layers of distance, distortion, and dust. And sometimes those layers hide more than just size. Sometimes they hide the very nature of what we're looking at. So we've seen how hard it is to measure a star. But even if we could, what exactly are we trying to measure? What do we mean by largest? Is it the star that takes up the most space, the one with the most mass, or the one that shines the brightest? The truth is, these are three very different things. Let's start with size, or volume. This is what we usually picture. A star so huge, its outer surface stretches past Saturn's orbit, like Stephenson 218. But here's the twist. Many of these enormous stars are mostly empty. Their outer layers are extended and diffuse, like a balloon inflated to the edge of bursting. Impressive, yes, but not necessarily heavy. Now consider mass. Some stars are far smaller in volume, but they carry much more weight. They're compact, dense, incredibly intense. Imagine two objects, a beach ball the size of a house and a steel sphere the size of a car. One looks bigger, but the other is heavier by far. That's how stars can be deceptive. Then there's luminosity, how bright a star appears from Earth. Brightness depends on temperature, energy output, and how far the light has traveled. Some stars burn furiously and die young. Others burn slowly and last for billions of years. And sometimes the faintest ones are the most stable. So when we crown the largest star, what are we really celebrating? A fragile giant, floating in space like a cosmic balloon? A dense powerhouse packed into a tight shell? A blinding flame that burns out in a few million years? The universe doesn't give us one easy answer. Each definition reveals something different, not just about the star, but about us and what we choose to value. Do we worship size? Do we chase mass? Do we stand in awe of light? Maybe the better question isn't, what's the largest star? Maybe it's, what does it mean to be large at all? What if some of the giants we've discovered aren't stars at all? It's a strange question, but in astronomy, strange questions often lead to better answers. When we look up at the night sky, we see light, brilliant, ancient, filtered through dust and time. But we don't see structure. We don't see depth. We see only what that light allows. And sometimes light can lie. There are objects out there that look like single, massive stars, unimaginably bright, impossibly large. But when we look closer, they begin to unravel. In some cases, what seems like one giant star is actually a tight cluster of stars. Dozens, even hundreds, packed so close together, their light blends into a single point. At thousands of light years away, even our most powerful telescopes can't always tell the difference. These are stellar imposters. But the trickery doesn't stop there. Some giants we see might be shells of stars, not stars themselves, but the glowing remnants of stars that have already shed their outer layers. Imagine a soap bubble, thin and delicate, floating in the dark, catching just enough starlight to shine. To our instruments, that glow looks like a star, but inside, there's nothing left. Other times, the distortion is entirely ours. Two stars along the same line of sight can appear to overlap, tricking us into seeing a single massive object when there are in fact two unrelated stars separated by vast distances. And then there are the things we haven't even imagined yet. What if some of the brightest lights in the sky aren't powered by fusion, but by something else entirely? What if they're not stars, but mistakes? artifacts of our tools, our models, our assumptions. In science, we often build conclusions on the best data we have, but the best data is still incomplete. So when we crown the largest star, we should ask, are we seeing a giant or are we seeing a ghost? If the stars are deceiving us, maybe what we need is a better set of eyes. And that's exactly what we're building. The next generation of telescopes won't just improve what we can see, they'll redefine it. One of the most promising is the Vera C. Rubin Observatory, a wide-field survey telescope designed to scan the entire southern sky every few nights. It won't just spot new stars, it will catch changes, it will record flickers, pulses, shifts, allowing us to watch stars evolve in motion, not just in theory. For the first time, we won't just ask how big is that star, we'll ask how is it changing. And then there's the James Webb Space Telescope, already in orbit, already delivering. With its powerful infrared vision, Webb can see through cosmic dust to the structures hidden behind it. In the images it's already captured, we're seeing galaxies form, stars ignite, and light that's traveled across almost the entire age of the universe. And that's just the beginning. Coming soon is the Nancy Grace Roman Space Telescope, engineered for deep sky surveys. Wide, sharp, fast, it will give us a clearer view of stellar populations on a scale we've never had before. And then there's the Extremely Large Telescope, a project so ambitious it sounds like science fiction. With a primary mirror over 39 meters wide, the ELT will let us resolve individual stars in galaxies tens of millions of light years away. Together, these instruments will give us more than answers. They'll give us perspective. We'll be able to distinguish giants from ghosts, stars from imposters, truth from illusion, and maybe, just maybe, they'll reveal something we never thought to look for, not just the largest star, but the most important. Because when we open our eyes wider, we don't just see more, we see differently. Everything that lives must one day end, even the stars. But when giants die, they don't go quietly. These colossal stars, Stephenson 218, VY Canis Majoris, UY Scuti, they burn brighter, faster, and harder than their smaller cousins. They live for only a few million years, a blink in cosmic time. And then they run out of fuel. At the core of every star, fusion holds gravity at bay. It pushes outward, a constant defiant force. But when the fuel is gone, the balance shatters. Gravity wins. The core collapses in on itself in a fraction of a second. Temperatures spike, pressures explode, and then comes the final breath, a supernova, one of the most powerful events in the universe. In a single moment, the star releases more energy than the sun will emit in its entire lifetime. Its outer layers are blasted into space, enriching the galaxy with heavy elements, iron, gold, uranium, even the carbon in your body, all of it, born in death. What's left behind depends on the star's mass. Some collapse into neutron stars, incredibly dense, city-sized spheres, so heavy a teaspoon of their matter would weigh billions of tons. Others fall even further, into black holes, points of infinite density where not even light can escape. And in some rare cases, a dying giant might tear itself apart completely, leaving nothing behind but light, shock waves, and dust drifting through space. It's tragic, it's violent, and it's beautiful. Because without these explosions, we wouldn't be here. The oxygen we breathe, the calcium in our bones, the iron in our blood, None of it exists without the death of stars. In that way, giant stars are not just distant bodies, they are ancestors. So when we look up at Stephenson 218, we're not just seeing a star, we're witnessing a future memory, a sun that will one day explode and scatter its atoms across the galaxy. And perhaps, one day, those atoms will become something new, a comet, a moon, a planet, a person, a single heartbeat, powered by the final light of a dying star. It's easy to think of giant stars as distant curiosities, beautiful, impressive, but far away and far removed from us. But that's not true. These stars, the largest, the brightest, the most explosive, are not just part of the universe. They've shaped it. They've shaped everything. In their cores, heavy elements are forged, not just hydrogen or helium, but carbon, nitrogen, oxygen, iron, gold, platinum, the building blocks of everything we know. These elements don't appear out of nowhere. They are born in heat and gravity, created in the pressure of dying giants, and then they are scattered. Each time a star explodes, it sows the galaxy with the seeds of future worlds. The planets we walk on, the oceans we sail, the air we breathe, all of it, assembled from stardust. Even life itself, the DNA in your cells, the calcium in your bones, the hemoglobin in your blood, none of it exists without the death of stars. In that way, giant stars are not just distant bodies. They are ancestors. They are our origin story. And they are still shaping the universe, guiding the formation of galaxies, triggering waves of starbirth, seeding molecular clouds with the ingredients of life. To understand them is to understand where we came from, and maybe where we're going. Because one day, our own sun will die too. Not in a grand supernova, but in a quieter, softer fade. Still, it will return its matter to the galaxy, and that matter will go on to become something else, something or someone. So when we look up at Stephenson 218, we're not just admiring a star, we're witnessing the life cycle of creation itself. The universe isn't just out there, it's in us. And maybe that's why we keep searching, why we climb mountains to see the stars, why we build telescopes, launch satellites, and dream beyond our reach. Because deep down, we're not just looking for distant giants, we're looking for home. In the end, what are we really searching for? A number? The largest star? The farthest object? The brightest light? Or something deeper? Maybe we're not just measuring stars. Maybe we're measuring ourselves, our longing to understand, our need to reach, our refusal to stop asking questions, even when the answers keep slipping through our fingers. Because even when the data is fuzzy, even when the sky is too dark, we look anyway. We search anyway. Not because we expect certainty, but because the mystery is part of the meaning. Stephenson 218 may be the largest star we've ever found, or it might not be, and that's okay. What matters is that we're looking, that we're curious, that we're willing to wonder, because every time we chase a distant star, we get a little closer to understanding where we came from, and maybe where we belong. Thank you for joining me on this journey. I'm Orion, and this is Infinite Universe NTH.